Okay, having explained a few methods of setting a turning tool to sensor height, I'm now going to attempt to explain why it's important, what some of the variables are, and some of the considerations to make when machining and when setting sensor height and so on. So what I've drawn here is a fairly standard turning tool. It's held in a tool holder, so that's what this is supposed to represent here, and I've just shown the end of it really, so there's more to it, but I've just cut it off here for the purposes of this sketch. And but it represents a turning tool that looks something like this. So this is obviously an insert tool. Here's the insert here, this is the shank, but obviously not all turning tools look like this. Some have brazed tips and some are made from high-speed steel. But anyway, this is the type of turning tool that I use mostly. And so as I've drawn it in the sketch, that's really what it's representing. So it's representing a tool being viewed in this elevation here. And for the purposes of what I'm going to explain first, what I'd like you to try and imagine is that I'm presenting a machining scenario a bit like planing or shaping, where the tool is perpendicular to the workpiece. So if you imagine this tool is perpendicular to the page and it travels laterally across it like this, and as it goes it performs the cutting action. And this is what I'm going to attempt to draw for you now. So but first, just a couple of just some terminology that pertains to the cutting tool geometry. So this surface here is ground back at this angle, and this is called the rake angle. So that rake angle is struck between this top flat face of the tool and then this facet that's ground on here. And then this face here, that's called a relief angle, and that will become more apparent in a second. So what I'll do to begin with is I'll just draw in the workpiece surface that has been machined here. So I'm trying to draw without knocking the tripod over. And then here, let's draw this in here. This is the surface yet to be machined. Okay, and I'll stop just short of there. So for the purposes of this sketch, the tool is moving that way in relation to the workpiece, and the workpiece is moving this way in relation to the tool. So they're passing each other like this. So this is where the chip forms at this point here. So I'll draw a chip in here, and the inside radius of the chip has a crinkly kind of finish to it, and that's because it's being compressed on the inside of the bend and it's being stretched on the outside of the bend. And across here, I should have come down a bit further, but across there it's a very small line that you may not be able to see that very well in the video, but there's a theoretical line across here, and depending on the material, these chips will either be very long spirals of swarf, or they'll be very short chips. So compare aluminium, which will produce lots of long ribbons of swarf, compared to something like brass, which produces very short chips. And it's at this point here where the chip ultimately fails and then flies off over it. Normally, if it's as I was taught in college, if it's hot, it'll go down the back of your neck, and if it's cold, it'll go straight in your eye. That's generally how it works. And but anyway, this plane here is called the shear plane, and the size of that and the angle of that is dependent on two things. It's dependent on the depth of cut, which is defined by this dimension here. Okay, so it's defined by the depth of cut, and also the feed rate, and also the material itself. Now, as this chip is formed, there are two reaction forces that will be experienced by the tool. So there'll be a reaction force that pushes the tool away from the work that way, and there'll also be a reaction force that pushes the tool downwards. So I'll just draw that there like that. So we could call that Fx maybe, or reaction force in the X plane, because that's the direction that that force is pushing in. And I won't call this Z or Y at this point. I'll just call that a reaction force. So I'll just call that Fr for now. Okay. And I mentioned before that this surface here is a relief surface, so I'll just draw that in there, and then that's that angle there. So that's a relief angle, and the purpose of that is to make sure that this surface of the tool doesn't rub on the workpiece. And now, the important thing to note here is that with this tool, it's important for this tool to be perpendicular to the workpiece. So if we were to imagine a line here, a dimension line from here, back here, so this is the dimensioning to the bottom surface or the top surface, just some reference face on the tool. That angle there is 90 degrees, so we draw that as a right angle. If it isn't at 90 degrees, in other words, if the tool is like that relative to the workpiece, or like that relative to the workpiece, then there's two different scenarios there. So when it's in that orientation, then you can see that the cutting tip is pulled away from the work, and the relief angle now contacts the workpiece. If we tilt it that way, then what happens is we reduce this rake angle and we put what's called either neutral or negative rake. And for most materials, you always want to have a positive rake, which means that the angle always drops away below the horizontal. If it's negative rake, then the angle goes above the horizontal. That's typically used for hard materials, so hard turning uses a negative rake. But for unhardened ductile materials, we'll always use positive rake. Okay, so the reason for explaining that is because it's easier to visualize what's happening here when machining a flat surface, so planing or shaping. But all of these principles relate directly to turning, and I'll explain why in a minute. So there are certain variables at play here, and so some of these are the tool overhang, so the distance from here, or rather from here to the cutting tip, so that's the overhang of the tool. And the longer that distance is, it's always advantageous to make that distance as short as possible. But the longer it is, the longer this lever becomes, and any deflection in this tool becomes more pronounced because the length is increased. So we always aim to keep that to a minimum. So that's one of the variables. So the first one is tool overhang. The next is the tool stiffness. I'll include thickness with that as well. So the thicker the tool, it stands to reason, the thicker the tool, the stiffer it will be. That's pretty obvious, I think. And then the next is the cutting geometry. So what do I mean by cutting geometry? Well, things like rake angle, depth of cut, feed rate, tool geometry, workpiece material, tool sharpness or tool wear, and tool material or tool coating. So these process variables, they significantly affect the cutting action. Now, I haven't included spindle speed because that's generally linked to the feed rate. Okay, but not necessarily so, because you might be roughing by hand, but I've assumed that these variables pertain to an automatic feed scenario. Okay, so now I'll explain, there's one of these variables that stands out that is worth, well, there's a few actually, so let me just run through them. So rake angle, certain materials prefer different rake angles, and so we can look up what they are. I won't list them here now, but the depth of cut, that can affect the reaction forces on the tool. The feed rate definitely affects the reaction forces. The tool geometry, I'll come back to this point in a second. Workpiece material, definitely. A harder material will offer more resistance to cutting, therefore for equivalent work done, i.e. volume of material removed in a given period of time, harder materials will incur much higher reaction forces. Tool sharpness or tool wear, a tool that's lost its edge will require higher force to do the equivalent work of a sharp tool. And tool material and tool coating, so some tools have titanium nitride coatings, which are a low friction coating. That can be very helpful to reduce tool wear because friction is reduced. But tool geometry is the point that I'm going to come back to now. Okay, so I've drawn two different scenarios here. The one on the left is a turning tool with a small corner radius, and the one on the right has a large corner radius. And they both present very different scenarios, and I'm going to try to explain the difference now. So as a blown up view of what's going on in here, then this, if I draw this radius here like this, so this is a magnified view of what's going on there. Okay, and so what we find is that we have a relatively small area. So if I draw the size of a chip next to the tip there, so as the tool advances this way along the workpiece, with it rotating this way, like that, then we have this relatively small surface area, which is going to be forming the chip here at the tip of the tool. In this scenario here, if I draw this in comparison, what we have here is a much broader sized chip. So if I draw that like that, and so the chip size is much bigger here because the radius is larger on the tool. And this is just a hand sketch, so obviously it's not to scale. But the principle is this. All materials have a shear stress value, and it will be different for all kinds of materials. The shear stress, or the strength of a material like steel, will be considerably higher than that of aluminium, let's say. And so the shear strength of the material is given by the symbol theta, which you might not be able to see. I might have not drawn that big enough, so let me try again. So it's not theta, it's sigma, lowercase sigma, equals the shear strength. Okay. And there's an equation that we can use here. So sigma can also be applied to, is the symbol of stress. So stress is equal to force over area. And this is an important thing to understand. So the strength of the material doesn't change. I'm going to say it doesn't change at room temperature. Let's, within tolerances of plus or minus, I don't know, 5 degrees, let's say. Let's assume that the strength of the material doesn't change. It does change with temperature, but we'll neglect it for these purposes. So I'm going to say that the tensile strength of the material is constant. In that case, if we have the same material in both of these scenarios, then with equal machining parameters, so the same feed rate, the same spindle speed, the same depth of cut, then what we find in this situation with a tool that has a small radius compared to large radius, okay, we find that the cutting forces increase here, so please forgive the writing, and lower force here, so higher and lower force. And the reason for that is the area the cross-sectional area in terms of the size of the chip. So if the area increases and stress remains constant, then force has to increase. Okay, this is why on one of my previous videos I was speaking about plunge turning a thread, and where the threading tool looks something like this, and where the chip is formed all the way around the tool here, and the result of that is high turning force. It puts a lot of stress on the machine. So why are we interested in force? The reason we're interested in force is that if I just quickly redraw the tool, okay, the higher the force, the more load that we'll be putting on the machine, the more load we'll be putting on the tool. If I'm clever about this, I'll try and insert a video clip or a picture of my solid tool post mount, which removes some of the deflection that can occur in the compound slide on my small lathe. And this is one of the reasons in terms of static loading on the tool. So the longer this tool hangs out from the tool holder, the greater the leverage. The greater the leverage that force has to act upon, the higher that this potentially can deflect. So from the point where it ceases to be supported by the tool holder, so if there is a force acting down on the tip, and there is when it's under load, then what happens is that there is a bending moment applied to it, and the bending moment is equal to force times the length. The longer the tool and the higher the force, the greater the bending moment. The more that this tool has to overcome deflection. So why am I talking about deflection? Okay, so the reason for it is that when we set tool height in a static situation, we are assuming zero deflection during the machining cycle. And this isn't true, because what actually happens is that the tool does deflect during machining, and that will change depending on whether we're roughing, whether we're finishing. It will depend on the tool geometry, it will depend on the sharpness of the tool, it will depend on if it's cast iron. Sometimes you can have a hard skin on the cast iron, and then you get into the softer material, and all of this changes the dynamics of the turning process. So I explained a few things before relating to a flat surface. Now I'm going to put it into the context of a round surface. Okay, so here's our round piece of bar. You have to imagine that we're looking at it from the perspective of the tailstock. Okay, so there's our round piece of bar, and what we're aiming to do is to have the turning tool exactly on the centre line. Sorry, let me try again. I messed that up straight away. So there's our turning tool, absolutely bang on centre. And we might achieve that really well in an unloaded state. But the problems arise when we have a long extension of the tool. So if we're holding the tool back here, and I see this a lot, and I'm not going to criticise anybody's machining videos at all. I do see it from time to time where I see that the tool is hanging out quite a long way, and the tool should be supported as close to the business end as possible to reduce this bending moment. But what can happen, there's two things. So if the tool is too high, then that's the equivalent of, oops, let me bring it back down here. If the tool's too high above the centre, then that's the equivalent of leaning the tool downwards, upwards like this, and we don't get efficient machining because our clearance face is now coming into contact with the workpiece. When the tool is too low, we have the opposite. So that's the equivalent of tilting the tool that way. And the result is we diminish our rake angle, and now we're going into the realms towards negative rake. And then that diminishes our machining efficiency. So what we want to do is keep our tool exactly normal or square, perpendicular to the local normal on a round piece of material. We know in a static condition, we know that there are various ways to measure this. We can measure the overall height, we can measure how well it is aligned to the tip of the centre. We can even put a rule in here and get it to line up vertically on the machine. There's methods that we can use, but what really matters is that the tool is at centre height during normal machining conditions. And one way to do this is to have a roughing tool, because roughing, if you were to standardise with a standard depth of cut for certain materials, that would be one approach. And because the forces are going to be higher, you might choose to set the tool slightly above centre height, because when it undergoes those high forces, it then drops down and compensates. For a finishing tool, you might have a different tool assigned for that purpose, more closely aligned to centre height, because the forces are going to be lower, therefore the deflection is going to be lower, and there's less to compensate by. So that's those are some of the principles to be aware of, and that's why sometimes we might not get the kind of finish we were expecting. We might not have the sort of machining efficiency that we were expecting, and we might go back and double check tool height and find nothing wrong, when in actual fact it could be another reason for this could be that we've got the wrong combination of tool geometry for that particular material. Some of these inserts don't have a dead sharp corner, so some materials like brass like to have a nice sharp tool, aluminium likes to have a nice sharp tool. Materials like stainless, they prefer something that has a less dead sharp corner. They can machine more efficiently with other geometries. All of these things come into play. So I hope that this little explanation has been useful and adds hopefully a bit of context to some of the considerations when setting tool height in a particularly a centre lathe turning application.